Another way to make our standard kinematic problems a little more tricky is to involve two objects. So far we've only been looking at one single object at a time, but we could have a problem that involves two objects that are going to meet. So let's think about how we're going to solve those problems. We're going to define variables for each object. So the position of each object, the velocity of each object, the acceleration of each object, and that can be different, okay? Be careful about positive and negative velocities. For example, if you have two objects that are moving towards each other, one of them has to have a negative velocity because when two objects move towards each other, they're moving in opposite directions. One's going the positive direction, one's going the negative direction. So make sure you take care of that. When objects meet, their positions must be equal. So the x position of object A is equal to the x position of object B when they actually meet. And so the general way we're going to solve these is we're going to use a kinematic equation for each object. So we'll have two sets of equations, and each of those equations will have two unknown variables. One of the unknown variables will be the position when they meet, and the other unknown variable will be the time when they meet. So we'll have two equations with two unknown variables, and then we can solve those using algebra. So let's look at a problem here. Press pause, do your best to define all your variables. Take your time as much as you can, and then press play to go through it with me. So I'm going to start by drawing a picture, just a really simple picture, because it's one thing to say, okay, Chicago and Pittsburgh are 640 kilometers apart. That's not quite going to help me. What I really want to do is set up a coordinate system with an x equals 0. So what I'm going to do is I'm going to say, let's pretend that Chicago is at the position x equals 0. Then that means that Pittsburgh is at an x position of 640 kilometers. I'm doing it all in meters, so that's 640 times 10 to the 3 meters. The reason I'm putting in meters is because we always do, and I know these speeds in meters per second. So now I'm going to say train A is leaving from Chicago traveling east. So train A is going this way, and train B is leaving Pittsburgh and traveling west. So I'm just drawing that. The reason I do this is now I can very clearly say that train A has a positive velocity, whereas train B has a negative velocity. So I got that out of my picture. Okay. Another thing to notice about this problem is that it's a uniform motion problem. It's uniform motion because these trains are not accelerating. That means I can use the very, very simple equation delta x equals v delta t. So that makes the math a little bit easier. I'm going to set up my information table kind of like this. I'm going to say event 0 is when the trains leave the cities, and event 1 is when the trains meet. So T0 is 0. I don't know what time they meet though. And here you can see I put X0A. That means the position of train A at this event. And now I can be really clear. Where is it? It's at x equals 0. That's where it starts. And the velocity of train A, which doesn't change, is 27 meters per second. So I put the velocity here and here. It's the same. Now here's something interesting. X0, so that's the X position at this event for train B, is right here, which is an X position of 640 times 10 to the 3 meters. So that's what I put there. And as I mentioned before, the velocity of train B is negative because it's traveling to the left, which based on my number line, that's the negative X direction. So I have to make that negative. This value doesn't change because it's not accelerating. Now, when the trains meet, I don't know what time they meet, and I don't know the position when they meet. I do know, though, that this x1a has to be equal to this x1b, and we'll get to that in a second. This x and this x are equal when they meet, but I don't know what that value is. So I'm going to write an equation, a kinematic equation, and actually it'll just be the simple uniform motion equation, delta x equals v delta t. But I'm going to write one equation for train A, and I'm going to use train A, delta x for train A, v for train A. Delta t is the same for both of them. So the basic uniform motion equation is delta x for train A equals v for train A times delta t. Well, what is delta x for train A? I'm going to separate it now because I want to put this in there because this is equal to this. So I'm going to expand. Delta x is just x1a minus x0a. The rest is the same. Now I'll plug in all the values I know from my table. x0a is 0. I don't know the position of train A when they meet. VA, the velocity of train A, is 27, and delta t is unknown. Here I've just simplified the math. So I don't know this value, and I don't know this value, so I cannot solve this equation yet. Let's write a similar equation for train B. I start with my uniform motion equation. Here I've just expanded that delta x is equal to x1b minus x0b. And now I've plugged in for x0b is the 640 times 10 to the 3 meters. And I've plugged in for my velocity. And then here I just rearranged it. I just brought this over to this side. Okay? So now I don't know x1b and I don't know delta t, but I'm getting close because I can say when the trains meet, x1a equals x1b. That means this equals this, or I can just set this part here equal to this part here, and then I have one equation with only one unknown variable, and that is delta t. So now I can use algebra to solve for delta t, and I get 14 times 10 to the 3 seconds. And the question though asks where will they meet? So to figure out where, that's really asking like what's this value? I need to plug delta t back into either this equation or this equation. Let's plug it back into this equation. So that's what I've done here. 27 times my delta t, and I get 380 times 10 to the 3 meters. That's the x position. So that is describing a distance that is east of Chicago, right? Because I put Chicago at my x equals 0. So the trains meet after this many seconds, which is about 4 hours, and it's this far away from east of Chicago. That's where they meet. Let's do another one. This one will be a little trickier. This one involves objects that are accelerating, or at least one of these is accelerating. So press pause, do your best to work through it the way I had done previously, and then press play to go through it with me. So again, I'm going to start by setting up a coordinate system. I'm putting Mario initially at x equals 0 and Wayne initially is at x equals 15. This is just how I set it up. And that Mario is going to be traveling to the right, Wayne is going to be traveling to the left. I want to make sure that I make Wayne's velocity negative since he is traveling to the left. Here's my motion information table. I have my event 0 is when Mario starts at the blue line. That's right when the players are 15 meters apart and he starts to accelerate. So that's kind of when Mario starts to accelerate. And event 1 is the collision. So I put I starting at t equals 0. Mario is at the position x equals 0 and he has a velocity at this moment, at this event, of 1 meter per second. This is going to change because Mario does have an acceleration. For Wayne, he starts at a position of x equals 15 meters and he has a velocity that is negative. It's negative because it's going to the left. And I had to put that negative in there. So he's also going to maintain a constant acceleration. Sorry, he's going to have a 0 acceleration, which means his velocity over here is the same. I don't know what Mario's velocity over here is. So the question is, how long does it take before they collide? That's like asking about delta t. And where do they collide? That's like asking the x position. It could be x1 Mario or x1 Wayne, either one. So we're going to solve this by doing what we did before. We're going to start by writing an equation for Mario, let's say. So in this case, I need to use my full kinematic equation. It's not the simple delta x equals v delta t that we had previously because there is an acceleration here. So I chose this equation because I want to deal with the displacement because that's how I'm going to incorporate this value. I want to deal with time because that's how I incorporate this, which shows up in both Mario and Wayne's equations. And then I know my acceleration and I know my initial velocity. So this is the basic equation I'm going to use. I'm going to expand the delta x to be x1 minus x0. And then I can just plug in the values that I know. And I get something kind of simplified here. I've just simplified things. Let's do the same thing for Wayne. So I'm going to use the same general equation here. For the delta x, I'm just remembering that's x1 minus x0. and the v initial will be his 0 velocity that I had here. So here I've plugged in for x0 Wayne, his initial position. I've plugged in for his initial velocity. His acceleration is 0, so this whole term just goes away. And I've simplified things here. So at this point I have 2 equations with 3 unknown variables, and the last thing for me to do is recognize that they are in the same position when they collide. So now I can just set this thing here equal to this thing here, and there I've done that. And then I'm going to solve it. How did I solve it? I have to use the quadratic formula. Okay, so don't forget how to use the quadratic formula. You need to use it. Go back and review that. So now I've answered the first question. How long after Mario crosses the blue line do they collide? 3 seconds afterwards. Where do they collide? Well, that's like solving for x1. So I need to plug back in into one of these equations. Let's do it here because it's easier. I just can plug in delta t is 3. And that's what I can do here, and I get 12 meters. Well, what does it mean 12 meters? That's the coordinate system I set up where x equals 12. That means it's 12 meters to the right of my x equals 0, which is what I call the blue line. Or you can say it's 12 meters to the right of where Mario started, is another way to say it. And there we go. That's it.